I'm Margaret Matthew. I'm with AISC. I'm their moderator today. This is our session on our upcoming brand new Design Guide 32 on AISC N690, our nuclear specification, the Appendix N9 on SC walls. So this design guide is almost out. We wanted it to be out in time for this presentation. It's not yet. It will be out in a few months and available. So I like to remind everybody now might be a really good time to silence your cell phones. So we do have both of our authors are here with us today to speak about our new design guide. Dr. Amit Varma is a professor in the Lyles School of Civil Engineering and a university faculty scholar at Purdue University. Dr. Varma received his PhD from Lehigh University. He served as the vice chair of the AISC TC12 subcommittee that was responsible for the development of AISC N690, the standard for modular composite construction for safety-related nuclear facilities. He's currently the chair of the AISC TC8 fire committee. And our second speaker will be Sahas Bhardwaj. He is a PhD candidate in the Lyles School of Civil Engineering at Purdue University, and his research focuses on the use of steel, concrete, composite structures in safety-related nuclear facilities. So if we could welcome Dr. Amit Varma.
Thank you, Margaret. Very good morning to all of you. Thank you for taking the time to come to this session. We'll get started. We have a 90-minute session, and my goal, we've broken up the session into 3 parts. We're going to have an introduction for about 10 minutes. I'm going to introduce the system and how it was developed, the specification and the design guide. And then I'm going to have Sahas, who's really the primary author of the design guide. He's done all the work. Present the design of the walls themselves. That should take about 30-35 minutes. And then I'll come back to talk about the design of connections. That should take another 30 to 35 minutes. So by 75 minutes, we should be wrapping up our talk, and we'll have about 15 minutes for questions and answers, and I'm sure there'll be plenty. All right, so let's talk about the Design Guide 32 and the AISC N690. Steel plate composite walls they've become almost commonly used in modern nuclear construction. There's some advantages that I'm going to talk about. I'm going to introduce the system and how they have been used in nuclear structures. But I'm going to talk about the consensus standard that we've developed, the AISC N690 S1. That's supplement number 1, published in 2015. I'll talk about its background, the layout, and the organization. And then most importantly, get to the design guide, talk about its scope, layout, and organization. And then we'll start with a design example of SC walls, which will be done by SAS. Now, SC walls, the motivation for their existence comes about from the history of construction methods. We have been trying to accelerate our construction schedule for several years now, for several decades. We started off with reinforced concrete, looked at slip forming, steel deck construction, and then slowly arrived at modular SC construction. The reason for that is, of course, the rebar congestion that one can get when you're designing using reinforced concrete. Particularly for nuclear structures or even for high-rise buildings now, you will find that the wall reinforcement ratio reaches about 1 to 2%. As soon as the wall reinforcement ratio reaches about 1%, you start getting reinforcement layouts that look like that, a lot of congestion. And of course, whenever I show this picture, the nuclear engineers tell me, well, that one's an easy one. It gets a lot worse than that. And this is actually a good one. And you're talking about rebar congestion here. The motivation is because rebar cages can be time consuming. You can virtually have a wall of rebar on the exterior surfaces, and then questions about concrete flowability and so on arise. So in order to address some of these topics, steel plate composite construction has been proposed and has been used in order to provide designs for nuclear facilities. And what we're looking at here is a typical SC wall. You're looking at 2 steel plates on the outsides and then concrete infill. So there is really no rebar needed in this particular design. The steel plates serve as the primary and the secondary reinforcement, but they are anchored to the concrete infill using either shear studs or using tie bars. And then you need the tie bars in order to provide communication between the two steel plates. As you know, in nuclear construction, the walls can get really thick. You can have 48-inch walls, 56-inch walls, sometimes even 60-inch walls. And 60 inches of plain concrete, you want to have a line of communication between the two steel plates so that they can communicate the stresses to each other. And that's why those ties are really required. Later on, when we get into the design example for SC walls, you'll see what else they provide to the design. SC walls provide an opportunity for embed plates, for commodity attachments, and also penetrations can be achieved right in the construction phase itself. So this contrasts the two systems, the modular RC wall, where you have prefabricated cages of rebar and then formwork. You'll have to first place the rebar cages and then the formwork, and then pour the concrete, then remove the formwork. Whereas for a modular SC wall, the steel plate itself is a stay-in-place formwork, as you're seeing here. And we've talked about the rest of the components in the system. It's relatively easy to accommodate embedment plates and attachments, and also sleeves for piping and so on. Modularity is really the key, and we have modularity as a structure and modularity from a construction perspective. It permits for prefabrication, pre-assembly, and modularization to reduce the construction time. The modularization of the steel modules themselves and the submodules allow for easy concrete placement, perhaps penetrations and attachments as well. This steel plate composite construction has been identified as part of the modular solution. I believe some of the newer SMRs are also utilizing these steel plate composite walls. Where have they been used in the nuclear industry? Just a listing of the project. It has actually been used by GE, Hitachi, and Toshiba in their ABWR that is located in Kashiwazaki, Japan, Kariwa, Unit 6 and 7. That was used in 1996. I've actually seen a mock-up of the steel plate composite containment internal structure in Japan when I visited MHI. They've been used extensively in the AP1000 plants that are being built in China, in South Carolina, and in Atlanta. The US APWR plant that has been designed by the Japanese and by MHI extensively uses steel plate composite modules. The APR Plus, designed by the Koreans, I was in Korea last week having a discussion with KHNP and KINS about their APR Plus design. They definitely are using steel plate composite systems there as well. And it is under consideration for SMRs. I believe both NewScale and Empower are looking at it. All use SC construction because of modularity, strength, construction schedule, and most importantly, the missile impact resistance that is provided by the armored construction itself. Since this is just an introduction to the system, now I want to take you to some pictures. I want you to get a sense for what these modules look like. Some of you have been already involved with the projects and you know what these look like. These are some pictures from Sanmen in China. You're seeing a module that is being lifted up and being brought in and being placed in the site, inside the pit. These modules get really, really large fairly quickly. I'll draw your attention to something interesting here. You'll see these dowel bars sticking up from the concrete foundation. This is a picture from Sanmen, and the SC wall is being lowered onto this. You remember this detail. We'll talk about it about 40 minutes from now. The connection between the dowel bar and the steel plates, we'll talk about that when we get to the topic of connection design. Another picture, this is a fisheye lens view of inside that's the containment vessel dome that's going to be anchored into the concrete, and you're seeing the module being placed here at the site. This is a picture inside the module shop where you're seeing the CA20 or a part of it being built, being fabricated before it can be shipped out to the site. This is inside the module shop. The module shop was built so that these modules could be built. And this is a picture of the module being taken out. This is how big they get. This is a 1,100-ton CA20 module. The steel module has been fabricated with the plates, the studs, and the tie bars, and it is being shifted to the site for placement. This is where you're seeing that module being lifted by the crane and being brought down. And then here you're seeing it. You're seeing a pretty nice picture of almost the overall plant. We're seeing the steam generator compartments, the pressurizer, and of course the shield building going around it, the containment vessel going around it, and so on. It gives you an idea of how these systems are being used. But in order to use these systems, what we really need is a consensus standard. This was published in the August of 2015. This includes, that's AISC N690 S1, which includes supplement number 1. Appendix N9 focuses on the design of SC walls, and you would essentially use AISC N690 S1 instead of ACI 349 for the design of the structure. It includes specifications for SC walls and also the associated connections. This just shows you it's a consensus standard, so all the people who were involved in the committee that developed this standard includes people from the government, international collaborators, regulators, fabricators, and so on. So quite a wide variety of people who've participated in the development. And we started developing the specification in 2006, and it went on till about 2015. Just the cumulative man hours exceeded thousands of hours that were just in the meetings needed in order to develop this consensus specification. And there it is, AISC N690 S1 2015. It's a free download. You can download it from the AISC website, and it includes all kinds of cool provisions, and Sahas is going to talk about some of them, particularly for the design of SC walls. When you look at Appendix N9 in there, you'll see there are 4 sections, one on the design requirements, one on the analysis, and then the design of walls and connections as well. And today, we're going to talk about pretty much all 4 of them. The specification was great. It was a consensus standard that had been provided, but everybody felt that there was a need for a design guide that would explain how to use the specification in the design. So we've been working on it, really, Sahas has been working on it for the past 2 to 3 years. He's done a great job putting it together. It supplements the SC specification in the sense that it shows you how to really use it. We are expecting the design guide to be published sometime around June of 2017. It discusses the basis of the provisions and provides calculations that show how an SC wall can be designed. It also includes the design of a typical SC wall, and an SC wall to base mat connection is included in the design. This is what the cover of the design guide 32 is going to look like. And that's my cue for inviting Sahas to come up and talk about the SC wall design example, which consists of these 4 steps that he's going to talk about. The PDH code for the session was on the first slide, and I'll bring it up again. There's the PDH code 16376.
Thanks, Dr. Verma. Get started. You can come back in whenever you want. Okay. So Dr. Verma gave us an introduction into the system, into the history of the standard, and about the design guide. How is it organized? What we're going to do now is we're going to dive right into the design of SC walls, look into what are the important steps that you need to take care of when you start designing an SC wall. The first step would be your preliminary details. What would you start with? And how would you know where to get the parameters you need to start with? Your minimum requirements is the first step, where you would see if your parameters actually qualify as an SC wall. Can you use the appendix provisions to design that wall? The detailing requirements, which is basically the heart of your design, which is where you would decide what is your stud spacing, what is your tie spacing, what is the area of studs you need, what is the area of ties you need. Your analysis procedure, where we would talk about how would you model your SC wall, what stiffnesses do you need to consider, how would you get the analysis results, and calculate the required strengths. Finally, we would get to the design procedure, where we would talk about the calculation of individual strengths, the interaction of demands, and the demand capacity ratios and interaction surface. So we've got 5 steps basically, and we want to cover all of them in this session. So I would walk through some of them, I would jog through some of them, and probably have to sprint through the rest of them. And we can catch our breath once we are done. We'll start off with the preliminary details. These are typically based on the plant layout details. So the plant layout engineers would select the wall thickness and other parameters which for nuclear construction may be governed by the shielding requirements and the existing industry practice. And during this phase, what the structural engineers can do is they can recommend standard steel ratios and section details. Once the layout design phase is done, you have the layout finalized, you'll come to the detailed design phase where you can check, design, finalize, and optimize your SC design. And what we're going to do in this session is we're going to consider a typical SC wall and design it. We'll go through all the steps of the specification and see how you would use the specification. So the preliminary details for the example are we are considering the critical section of a wall, a portion of the wall from the refueling cavity with the elevations between 40 feet and 66 feet. The steel grade is grade 50, concrete is 5 KSI. You would get the operating thermal conditions and ambient thermal conditions for the plant. Other considerations for this example are we are not considering any openings or attachments for this particular wall. As Dr. Verma showed you, a typical SC wall, you would have openings in the walls and there would be attachments to the walls. And the specification also talks about the fabrication and construction tolerances, which are very important because of the size of the modules that you saw, you need to combine the modules. So they need to be satisfied. For this example, we are considering that those tolerances are met. So the preliminary details for the wall, The preliminary details for the wall, you get your unsupported height. This SC section thickness is what would be governed by the plant layout shielding requirements. And then your faceplate thickness, you can decide, so the structural engineer can decide, okay, I want to start with a particular reinforcement ratio, which would give us the faceplate thickness. And then the shear connector spacing and the tie spacing is, you would start with a typical value, and then once you start optimizing your design, you could optimize these values. We have our preliminary details. We want to see if the parameters we have satisfy the minimum requirements of the code, can we use the provisions of the code? So these requirements given in this section of the code need to be satisfied, and the basis is the provisions are based on a range of experimental data. And these requirements are for that experimental data. And there is a need for detailing the SC walls to prevent certain limit states or failure limit states from governing. And there's an EJ publication which is going to be out in the second quarter, which talks about all of these minimum requirements and the sectional detailing provisions and the basis for all of them. What we're going to do is we're going to verify that we are meeting these requirements. The SC thickness, we have a 56-inch thick wall, which meets the requirements. Our faceplate thickness is 1/2 inch, which meets the requirements. The reinforcement ratio, which is the ratio of the area of steel versus the total area of the wall, it meets the requirement. And the basis for all of these is discussed in the design guide. It's discussed briefly in the specification and in the publication we just talked about. You have the yield stress needs to be between 50 KSI and 65 KSI. For concrete, needs to be between 4 KSI and 8 KSI, and the code doesn't allow lightweight concrete as of now. Then we say we need to satisfy the detailing requirements, which we would talk about, what those detailing requirements are. The faceplate slenderness requirement, shear connector detailing, and the tie detailing. We'd start off with the faceplate slenderness requirement. So these detailing requirements ensure that these certain limit states of failure do not govern your design. The first one ensures that your stud spacing is limited so that the faceplate yields in compression before compression buckling. And that's the requirement. So you have your, where B is the largest unsupported length of the faceplate, and the requirement states as long as your slenderness, faceplate slenderness, which is the ratio of the largest unsupported length with the faceplate thickness, is less than root of E by F by, you meet the slenderness requirement. And I'm tempted to go into the basis of these things again, but all of that is available in the design guide. You can look at it. So for our design, we said the stud spacing is 6 inches and the tie spacing is 24 inches. And if you look at it, so you have your ties spaced at 24 inches, and then you have studs in between those ties, which are spaced at 6 inches. So the largest unsupported length for this configuration would be 6 inches. And it would be different for different configurations of studs and ties. So you can calculate the slenderness ratio, and you can check it with the requirement in BC that we meet that requirement. Next step we get into is the shear connector detailing. The shear connector detailing ensures that the stud spacing is limited to ensure the composite action in SC walls. You would start off classifying the steel anchors as yielding or non-yielding, which is based on the if the anchor can maintain an interfacial slip greater than 0.2 inches when the load is 90% of the peak load. For this example, we are using steel-headed stud anchors, which are classified as yielding. If you're using any other kind of anchors, you would have to perform experiments to see if they are yielding or non-yielding type of anchors. And if you have a combination of yielding and non-yielding anchors, the system is classified as non-yielding. For this example, we are using yielding anchors. The next thing in your shear connector detailing would be the spacing of the connectors. There are 3 criteria: the faceplate slenderness requirement, which we just looked at. Then there's the requirement to achieve a desired development length, and we'll talk about it, which gives you another spacing limit. And there's the third requirement to prevent interfacial shear failure from occurring before out-of-plane shear failure. And we would discuss that briefly. Let's look at this development length requirement. So this development length, similar to what is in the reinforced concrete word, is the distance over which the faceplate can develop its yield strength. And that would depend upon what is the area of steel anchors you provided and what is the shear strength of a particular anchor. And that's the requirement where C1 takes into consideration what we just discussed, if the anchor is a yielding anchor or a non-yielding. And that's the shear strength of the anchor. The designers can decide what is the development length. We have a recommendation, and I'll talk about that. And TP is the yield strength. Now, the development length has a direct bearing on the degree of composite action you can get. Zhang et al. Recommend that if you have a development length around 3 TSE, you can get about 75 to 90% of the partial composite action. So for our example, we'll consider the development length 3 TSE. Since we're using steel-headed stud anchors, from the spec we can calculate the available shear strength. But what is important is, in case you decide to use something else as a steel anchor, you want to use flat bars, then you would have to calculate the available shear strength from experiments. And you have your faceplate tensile strength, and using those values, and that's the factor which takes care if your steel anchor is yielding or non-yielding. And you see the requirement is satisfied. The next thing was interfacial shear. So we need to limit the stud spacing to prevent interfacial shear before the out-of-plane shear failure. We want to avoid interfacial shear failure mode. That's the spacing requirement. C1 again takes into consideration if it's a yielding or non-yielding. And VC is the available out-of-plane shear strength. That's the shear strength of the anchor, and that's the SE thickness. We need the available out-of-plane shear strength to check this requirement. We've not calculated. We don't have any available strengths as of now. So once we calculate the available strengths, we'll get back to this step and check this calculation. We've looked at the faceplate slenderness requirement. We've detailed the studs. Let's get to the ties. What do ties do? What is the purpose? As the name suggests, they tie the structure together. So they provide structural integrity by preventing section delamination or splitting. And Dr. Verma is going to show you a couple of figures when he gets to his presentation what we are talking about. So ties hold the section together. They serve as your out-of-plane shear reinforcement, so they are the shear stirrups of the SC wall. They contribute to the interfacial shear strength, and again, you would need to experimentally determine what is their contribution to the interfacial shear strength. They participate in the force transfer in the connection regions, and once you looked at those empty modules, the size of those modules and how they need to be lifted and transported, so they would help maintain the form of empty modules. The spacing requirement is the spacing needs to be less than section thickness. We said our spacing was 24 inches in both the directions, which is less than the section thickness, so we meet the spacing requirement. Next thing is the classification of ties. So their contribution to out-of-plane shear reinforcement would depend upon if they're yielding type or non-yielding type. And what you would see is we've kept a safety margin. And the safety margin is to ensure that there would be account that there would be a difference between the nominal and the measured properties. And that is what the safety margin takes care of. So, and the nominal strength would be either the rupture strength of the tie or the nominal strength of the connection, whichever of those is the lesser one. So for our design, we can calculate the tie rupture strength, we can calculate the tie yield strength, and what we considered was that the tie to faceplate weld is a CGP weld, so the connection would be stronger than the tie. So we can see if this requirement is satisfied, and we have yielding ties in our section. When we said what ties do, we said they prevent the delamination of the section, which means they would have some tensile strength requirement, and this is that requirement, and this is based on that postulated failure mode where the section can delaminate, which would happen if you just loaded one of the elements of the either you loaded the concrete or you loaded the steel faceplate. And so there would be an eccentric moment which needs to be resisted, and this force corresponds to that resisting moment. And we can check that. We have all the parameters we need. We have the spacing, we have the section thickness. That's the requirement, and we can check the tensile strength, the available tensile strength of ties, and we satisfy that requirement. So we've seen that, yeah, we can use the code. We've done the major part where we've detailed our section. Now we come to the analysis procedure where we would talk about what stiffnesses to use, how to model the SC wall. So there's a couple of very important words there. It's elastic, three-dimensional, thick shell, finite elements that need to be used. And the code specifies that you have to do a finite element analysis, and the reason is because you're talking about continuum structures. So finite element method is the only feasible method. You might need to do dynamic analysis for impactive or impulsive loads. The recommendations for finite element, your element size needs to be less than twice the section thickness for interior regions and less than section thickness for connection regions and around section penetrations. You need to check if you need to do a second order analysis. Typically it would not be required. Then you need to do analysis for accident thermal loads. Another important thing, since we are not doing that in this design example, I would like to talk about that as modeling your openings. So you need to see if it's a small or a large opening, and then the code and the design guide talk about the modeling and the detailing requirements for those openings. So that's a warning sign. It's going to turn off in some time. The openings can be detailed to have a free edge or a fully developed edge. So when you have a free edge, that means some region around the opening doesn't behave as an SC, and you need to accordingly consider that in an analysis. And a fully developed edge, you can consider that an SC right from the edge of the openings. So for our analysis, we did a 3D SC wall using elastic thick shell elements. So that's something I would like to talk about. So you've got an SC wall which has studs, tie bars, plates, it would have openings. And what you're going to model would be just a thick shell element, which means all you have, and it would be an elastic element, which means all you have to play with is the section thickness, the elastic modulus, and the Poisson's ratio. And the importance of this we would get to know once we talk about the model parameters as we go forward. The analysis model parameters, so we check the second order effects, we do not need to consider the second order effects. We have not considered any openings. We have performed the accident thermal analysis, and we'll discuss them. So we have the operating thermal conditions. And that's something important, and we'll talk about that. So there are going to be two conditions. So you would be doing two analyses. One would be for your operating thermal conditions, which we are calling condition A, and the second one would be your accident thermal conditions, which we are calling condition B. Let's start talking about the stiffnesses of the model. First would be your flexural stiffness. And you see there's the steel contribution, there's a concrete contribution, but there's a factor, C2. So what has been observed is that the uncracked stiffness is not manifest. There is due to shrinkage, cracking, and partial composite action. And this is the calibration factors which ensures that your stiffness is crack transformed stiffness. And then you see there's a temperature term, and once you go above 150, it's fully cracked, and the only stiffness you have is the steel stiffness. So we can calculate the stiffness of a section. We can calculate the moment of inertia for concrete, the moment of inertia for steel, and then the calibration constant is in terms of stiffness adjusted modular ratio, which we can again. So, like I said just a while ago, you would need to do two analyses. One would be your operating conditions, and the other one would be for your accident conditions. So you can calculate all the parameters, and this delta TS average, which is the average of the maximum temperature rise in both the face plates. For operating conditions, it's considered 0, and you can calculate your crack transform stiffness and your steel stiffness. Once you get to the accident thermal conditions, you would see that this term goes negative and your steel stiffness controls, which is what we said. In the accident conditions, it's fully cracked, and you just have the steel stiffness. Then we get to the in-plane shear stiffness, and this depends on what is your in-plane shear demand. If your in-plane shear demand is less than your cracking threshold, you have your uncracked stiffness. If it's greater than twice of your cracking threshold, you have your crack stiffness, and then you can interpolate. For this design example, so you don't have your demands before you do your analysis, right? So you need to assume, okay, my demand is this, my demand is this, and then do your analysis and verify. If you're okay, it's good, otherwise you would have to come back. For this, we consider we are in this region. And the basis is your in-plane behavior is based on steel plane stress and orthotropic cracked concrete behavior, and it's discussed in detail in the design guide. So we can, for condition A, we can calculate the crack stiffness using all the parameters. We can calculate the uncracked stiffness, steel stiffness, concrete stiffness, and then we can calculate, so the cracking threshold is considered as 2 root F prime C in PSI units. These are KSI units, so it looks a little weird. And this is what we assumed, that your demand is 1.5 times your cracking threshold, and then you can calculate your effective stiffness. For accident thermal conditions, it would be your cracked stiffness. And the basis is because you would have nonlinear thermal gradients which would cause concrete cracking in both the directions. So we've used cracked end plane stiffness for accident thermal conditions. Next we come to material properties. This is where everything would start coming together, what is going on. So remember, we have an elastic model, and for that model, the Poisson's ratio, thermal expansion coefficient, and thermal conductivity would be the properties of the concrete, because the concrete would govern your thermal induced displacement. The concrete is what occupies the majority of the volume. And then for that elastic model, what we want to do is, we have calculated these effective stiffnesses. We would calibrate our model section thickness and the elastic modulus so that the stiffnesses of our model match what we've just calculated. And then we would calibrate the density so that the mass of our model matches what the physical mass. And the specific heat is calibrated so that it matches with the specific heat of the concrete. So we have an elastic model where we are calibrating to match the physical model properties and perform the heat transfer analysis. So we'll quickly look at, so all these parameters are concrete parameters. And this is what I was talking about. So you have calculated your effective stiffnesses, and then you have your modulus for the model and the thickness for the model. You've got two equations. You can calculate the values for operating condition and for accident condition. Your material density, similarly, to match the mass of the physical model, and your specific heat to match the specific heat of the concrete. And this is what it looks like. So that could be a little confusing because you're not modeling a 56-inch thick wall. This is the thickness of your model for operating conditions and for accident conditions. So those are the parameters you're going to use. So that is why I said you're going to have two analyses. You're going to have two models, one for accident and one for operating. Let's talk a little bit about the thermal loads. So you would need to do heat transfer analysis where you would use the material properties we've just defined for accident loading. These analyses would give you surface temperature histories and through thickness temperature profiles, which would be nonlinear thermal gradient. So if it's a one-sided heating, you can see that nonlinear thermal gradient through the thickness, through the depth of the section. What we do in the analysis is we pick up these points and we use a linear thermal gradient for an analysis. So the thermal load is applied as a linear temperature gradient through the wall of the stress analysis. That is what we did for the example. We did the heat transfer analysis, and then the results from that would serve as an input for your stress analysis model. Let's talk a bit about the load combination. Chapter NB2 provides the basic load combination, and then based on the project requirements and the design basis document, you can have additional load combinations, and these load combinations imply linear superposition of demands. That is where it's again important why we have that elastic model. And then the combinations are there for condition A and for condition B. In operating condition, we do not consider concrete cracking, and in the accident condition, we consider the concrete crack. So those are the basic load combinations from N690. You see the operating T naught. So these are the condition A load combinations, and then these are condition B load combinations, 12, 13, and 14. So they have the accident thermal conditions. And then you could expand on them based on your project requirements. So these would be your basic load combinations. The specification does allow averaging over 2SC by 2SC in the interior regions and over TSC in the connection region and around the openings. The required strengths, so there would be out of plane flexural strengths, MX and MY. There would be twisting, MXY. There would be membrane axial strength, SX and SY and SRX. And there would be out of plane shear demands. So you'll have 8 demands that you'll get for each element. So the analysis results summary, we'll just talk about the summary of the results. We model the wall. We have the element size. We use 24 inches by 24 inches. So you would have all the data for each element, for each load combination, and then you would combine and evaluate that data. What we are doing is we're just looking at the peak demand for each demand type. and the element numbers, what you see is the accident thermal load conditions usually govern. And the peak demands are at the base of the wall. And averaging is permitted, but we've not done any averaging. And if you do remember, it's been a while, we talked about it. When we calculated the in-plane shear stiffness, I said we are assuming that it's 1.5 times the average demand. So that's the ratio of the demand versus the cracking force. And you see the average is around 1.5. So we are okay. We don't need to redo the analysis. What's the time? Okay, so this is when I would start sprinting. So that's the design procedure. What I want to do is quickly show you how you would calculate the individual available strengths, the demand capacity ratios, what are the interaction requirements in the specification. Let's start with uniaxial tension. It's governed by the lesser of the tensile yielding or the tensile rupture. You can calculate the available strength, and then you can calculate the demand capacity ratio for all the elements in the wall. You would do the same thing for the compression. You would calculate the buckling stiffness, and then you would go to the specification and you would calculate the compression demands. But if you look at it, you would see, and the last one is missing, it's very over-designed because the thickness of the section is based on the shielding requirements. And Dr. Verma is going to talk more about it, why this is important and how it would affect your connection design. Your in-plane shear is based on the von Mises faceplate von Mises yielding limit state. So you see there's a factor of 0.9. Kappa is the calibration factor, and you can calculate the in-plane shear demand, and you can get the demand capacity ratio for it. The out-of-plane flexure is again governed by the faceplate yielding and tension, the limit state of faceplate yielding and tension, and you can again calculate the demand capacity ratios for the out-of-plane flexure. Now the out-of-plane shear, it depends on what the spacing of your shear reinforcement is. If your shear reinforcement is less than half the section thickness, you can add the concrete and the steel contribution, which is what the case is for us, and we are adding. So the concrete contribution is 1.5 times root F prime C in PSI units, and then we have a steel contribution which is limited to 8 root F prime C in PSI units, and you can calculate the out-of-plane shear demand. And there comes the interfacial shear check. We needed this out-of-plane shear demand to check this interfacial shear requirement, and once we have that, we can check. So this is, in fact, this is what governs our shear strut spacing. It's 7.8 inches, and our spacing was 6 inches. Okay, the interaction of demands. So the specification says you need to consider two types of interactions. One is the out-of-plane shears and the interfacial shear demands. So we are going to pick just one element, one load combinations, all the demands. So it says if your out-of-plane shear demands are greater than the concrete contribution to the strength, you have an interaction. And that's the demand capacity ratio. We'll need 1.5 hours to explain this. So I'll skip this. And so you can calculate this demand capacity ratio and check if your interaction is satisfied. The second interaction it talks about is all of your out-of-plane moments and the in-plane membrane forces. So you have three in-plane membrane demands, SRX, SRY, and SRXY, and then you have your out-of-plane moments. So what it says is you require to evaluate this interaction for each notional half. What we've done is we've split this up into two notional halves, and the moments are considered as couples based on the lever arm, which would be decided upon what is the extent of cracking. And then based on that, you can calculate this S prime Rx, Rxy. So you see this momentum with the lever arm. You can calculate the principal stresses, and then based on which region you are in, one of these interaction equations would be applicable. We also provide the interactions in terms of in-plane. Now let's look at how does it look. So we've done just one element for one load combination. So you see that's where we've done just one load combination, all the elements for this load combination. and you see all the data points. So what we do is you have the demands, you calculate the principal stresses for all the elements, and that is your interaction surface. So you see there's one element lying outside and there's one right on it. So we would need to redesign the wall. Either we can use higher grade of steel, or you can average the demands for ductile limit states. Some things we've not considered here. We've not considered regions around openings. You need to do that. You need to design for impactive and impulsive loads. We do provide one figure to consider that, and then you need to, and that's important because of the size of the modules, you need to consider fabrication and erection tolerances in the design procedure. I can take a breath. Thank you.
Okay, thank you, Sahas. I think you did a great job in spite of the technical difficulty. So you got a chance to see how the SC ball is designed, and there are lots of details. It's a complicated and extensive design. But I think the takeaway are those contour plots that he showed for the elements, the demand to capacity ratios. That's a nice way to think about how you've checked the design and what it's showing you in terms of the capacities that are available. And if you look at it, when you get a chance to download the design guide and look at it and study it in more detail, you'll see that one of the highest demand to capacity ratios that he had was for out-of-plane shear, which was at about 0.56. And then that interaction surface, which accounts for all of them acting at the same time. There were some points that were getting outside of it. And so you would have different options. You may need a thicker plate, or you may need a higher grade of steel, or you may want to revisit that element and see what is causing that point to lie outside. In the third part of this presentation and the design guide, we talk about the design of connections. So design guide 32 focuses on the types of SC wall connections and some of the design challenges that SC connections and connection regions are going to have. So I'm going to introduce first the different types of SC wall connections. Then I'm going to talk about the connection design specifications, how we've addressed them in the spec itself. What are the connection demand types? What are the force transfer mechanisms? And what is really the connection design philosophy and the required sense? The design philosophy is going to be extremely important for the connection. What is the connection available strength and how you would go about calculating it. Then I'm going to show you examples of some typical SC connections. I'm going to talk about the wall to base mat anchorage. I'm going to talk about the wall to wall connection, wall to slab connection. What are some of those typical geometries and what do they look like? Let's talk a little bit about the design guide 32. This is going to be published, as I mentioned earlier, in the second quarter of 2017. It discusses the SC provisions and provides additional aspects of the design of SC walls. Now, the specification N690 itself does not go into detail of connection design. It provides performance-based specifications. So it tells you how you need to design and what is the performance that you need to get from the connection. But it cannot include details because composite structures, the connections can be very varied depending upon what you're trying to accomplish. You have to take the stresses from the steel plate, from the concrete, transfer it into the foundation, the rebar, and so on. So there are many different ways to effect an SC connection. So instead, what we chose was we saved it for the design guide. So the design guide includes more examples of connections and force transfer mechanisms, things that we can think about. By no means am I trying to imply that all the connections in the design guide are the ones that you need to use. You can look at the design guide, and once you understand the philosophy, once you understand how force transfer mechanisms are done and how the design checks are done, you're free to design your own connection for your own purposes. So the design guide does include some examples of typical wall connections and wall to base mat connections and so on. It's in the design guide itself. So let's start talking about, with the simplest connection, there are different types of connections we'll look at. The first one I'm going to talk about is the splice. You can have a splice between an RC foundation or an RC wall and an SC wall. And there are different ways to go about achieving the splice between SC sections and between SC and RC sections. In this case, we're looking at a splice between an RC and an SC section. And what you're seeing is that this splice is being achieved using dowel bars. We mentioned this earlier when I showed you photographs of the side. I said, keep an eye out on this dowel connection. This will repeat itself. So this is where we are splicing You're looking at a reinforced concrete portion underneath. You're looking at the dowel bars that are sticking up, and they're just lap spliced with the SC wall itself. The dowel bars are transferring the stresses into the steel plate, and the shear studs and the ties are accommodating that force transfer. That is one example of an SCRC splice. And we've done extensive work on these splices. We've done quite a bit of testing. We did some years ago, and then we're doing some tests right now, where we're looking at the force transfer mechanism between the dowel bars and the steel plates and the force transfer through the ties and the studs. That's what that test setup is about, how the forces are transferred from the dowel bars into the studs or the tie bars. But what this test also showed to us was that if you don't have ties that connect the two steel plates together, and you're trying to splice the RC portion with the SC portion, there is a potential for a splitting failure because of the eccentricity in the force transfer. Any lap connection, even if it is a welded lap connection, is going to have eccentricity. And you have to deal with that eccentricity. We usually get away with it because the wall thicknesses are not that large. But when the wall thicknesses become really large, the tension force is up here, but the reaction is down here. They don't line up, which means there's going to be an eccentricity. And that eccentricity generates the moment. And unless you have provided ties to connect the two sections together, it'll split open because it produces a tension field because of the eccentricity. Then there are wall-to-wall joint connections. If you look at your plant layout, there'll be many locations in which you'll have walls intersecting other walls, and you'll have, for example, a T-joint, or you may have an L-joint, or you can have an elbow joint of the type that you're looking at here. These are very real pictures from real plants where you can have these kind of joints occurring. And the question is, how do you design this connection between this wall and this wall? And in this case, we've called this the continuous wall and this the discontinuous wall. And that's just for the purpose of connection design. We'll talk about what the force transfer mechanisms could be and so on. The T-joint. And I'm showing you here some experimental setup where we were testing these T-joints, where you're seeing the continuous wall and the discontinuous wall that is connected to it. Our focus for the experiments was to look at the force transfer mechanism and eventually what would be the governing joint shear failure mechanism. You're looking at a close-up of that connection region. This is the continuous SC wall. This is the discontinuous SC wall that is brought in and welded to it. And you're seeing the shear studs. And there are no ties in this particular specimen that we tested. And if you look at some of our publications, you'll see that we tested specimens with one tie and two ties as well. L-joints, another example of an L-joint that is being tested in our laboratory. We're looking at a corner joint right here, and that corner joint with ties and without ties, and what that behavior is going to be like is shown here. A simple example of what that connection at the corner looks like with the shear studs on both sides of the continuity plates and so on. Anchorage of the SC wall to the reinforced concrete basement. This is a big topic. You can get the anchorage by using dowel bars, once again, that are sticking up from the foundation and directly spliced with the SC wall up here. And this is a similar example of a test where we're going to be looking at the in-plane shear behavior or the cyclic shear behavior of this kind of a connection where the forces are transferred from the steel plate into the reinforced concrete dowel bars and then back into the foundation. We'll talk about that. So here's an example, a photograph of the specimen that is being ready for testing, looking at that particular connection. And in this particular connection, all the inelastic action occurs at the steel plate to concrete joint interface. There is a lot of yielding of the dowel bars. The dowel bars were designed as the weakest link between the connection and the wall. There was a lot of energy dissipation, and we had good cyclic behavior from the specimens. And then, of course, there's the other type of design where you where you have a base plate that goes across the SC wall and then anchors that place it into the foundation. And in this case, the inelastic action occurs in the wall itself above the connection region. And we'll talk about what all of this means in a few minutes. So there's anchorage of the SC wall to RC basement. So there are many different types of connections. You can have splice connections, wall-to-wall joints. You can have anchorage of the SC wall to the basement, and then SC wall to the RC slab connection. This is a rendering of an example connection between a reinforced concrete slab and an SC wall. And in this case, the connection is being achieved with the help of rebars that are attached by weldable couplers to the SC wall itself. And inside the SC wall, we have rib plates and tie plates in order to provide continuity of force flow through the connection system. There are other types of connections that are also possible. In this case, we're using the same lap spliced system in order to transfer the stresses from the rebar into the steel plate, and then the rebar is anchored into the SC wall itself. So there are different ways to go about achieving these different types of connections. But these connections are fairly complicated, and there are a lot of challenges associated with them. What is the biggest challenge? The biggest challenge is that these connections are not similar to steel or RC structures, because the force transfer mechanisms can become fairly complex. Joint constructability and detailing requires careful consideration. Most importantly, there are no well-established rules, like you have steel or concrete connection rules that can be leveraged for the design of SC connections. That means you have to go about it carefully, looking at the force transfer mechanisms, what the constructability is going to be, and how they have to be designed and detailed. Some parts of it will be steel-to-steel connections, and some part of it will be concrete connections. They're more complicated as well. Typically, you're looking at beam-to-column connections where there's a shear and there's a moment that you need to transfer. But in these systems, you have a lot of forces. As Sahas was pointing out, each finite element in the wall has 8 demands. And when you get to the connection region, you have to make sure you transfer most of them from one wall to the other, or from the wall to the basement. So there are lots of forces that may need to be transferred as well. Unlike steel or reinforced concrete structures, SC walls have high in-plane shear demands, and the use of shear friction reinforcement just by itself may not be sufficient for the design. It's also not easy to embed rebar into the continuous plates in SC walls. It can be done in a few cases. And since SC walls are huge, connections may sometimes be designed to be weaker, in which case there is questions about whether there is adequate inelastic deformation capacity or not. The interaction of various demands will need to be considered, preferably on a small element basis. And the question, of course, is, am I going to achieve ductility? Local ductility at the connection and global ductility in the overall wall and connection system as well. When we talk about the connection region of the wall itself, SC walls and the systems that they're part of are labyrinthine. They're interconnected. They're connected to the base mat and the slabs. The connections use an assembly of connectors. They'll use steel anchors, ties, welds, bolts, etc. And these participate in different force transfer mechanisms for different demand types between the two connected parts. So for example, here I'm showing you a picture of a typical SC wall. And what do I mean by the connection region? As you can imagine, if this wall is connected to another wall here, or this wall is anchored into the base mat, over this region, you slowly transfer the stresses from this wall into the foundation. And you transfer the forces from the foundation into the wall. And over this region, you develop composite action between the steel plate and the concrete, because the stresses are becoming equalized. So this region, the connection region, we're saying this needs to be less than 2 times the wall thickness. Doesn't have to be equal to, it has to be less than 2 times the wall thickness. Preferably somewhere around 1 times the wall thickness. So if the wall is 3 foot thick, we would want the connection regions to be about 3 foot, by which time all the forces and stresses should be transferred, so that you can have this nice interior region where you can dissipate energy in the case of a beyond design basis event. So that's the purpose of these connection regions. And the stress transfer is to be achieved over that. It serves as the transition region for force redistribution. It also is the one where we develop composite action. And that's why I said the requirement is that it needs to be less than 2 times TSC, but we prefer that it should be about 1 times the wall thickness, because that will prevent detrimental congestion of steel anchors and ties. You can try to cram too many in order to make that connection region even smaller, but then you may end up with some congestion issues of your own. So let's talk about the connection design specifications itself. There are different connection demand types. I'll talk about that in a moment. Force transfer mechanisms that we need to identify, the connection design philosophy and how to calculate the required strength, and then finally the connection available strength. The connection demands are obtained from the same finite element analysis. When you model the structure, you model the entire structure using elastic, thick, finite elements. And when you have these shell finite elements, you're going to have all kinds of demands. But when you get to the connection region, you may need to look at the demands on a per unit length basis. For static loading conditions, condition A, and for condition B, you'll have all these demands. And these demands may be differentiated into seismic demands and non-seismic demands. For all the load combinations that Sa has showed you for condition A and condition B, some of them included seismic. And you keep the seismic demands, identify them, and keep them separately because your connection design philosophy requires it. For example, if you're looking at the connection region of a wall to basemat connection, you need to make sure that you transfer the axial forces, you need to transfer the in-plane shear forces, the out-of-plane shear forces, and the out-of-plane moments. From a connection design perspective, these are the four forces that you need to make sure that you transfer from the wall into the foundation or into the basement. For each of these, whether it's the axial force, in-plane shear, out-of-plane shear, or moment, a clear, identifiable force transfer mechanism needs to be provided. It has to be provided in order to design the connection. Each mechanism should involve connectors of the same type. We know that. We don't want to combine bolts with welds, and so each mechanism should involve connectors of the same type. It is possible that you may be using more than one mechanism to transfer one type of force. In that case, the one with the largest connection design strength will govern the strength for that particular mechanism. There are many different types of connectors that you can bring to bear. For example, stud anchors, tie bars, welds, and bolts. You can also come up with interesting connectors or fasteners of your own. The difficulty with that is if you are using a connector that has never been used before, then you'll have to do the tests to provide the data that identifies the strength of the connector itself. The specification clearly says that the bond between the steel plate and the concrete is not a valid connector at all. So one of the most important parts that we need to talk about is the connection design philosophy, because it completely governs the way the connection is designed. It is based on capacity design principles. The specification permits two design options for these connections. The first is a full strength connection. The full strength connection is such that the connection is always stronger. That means failure will never occur at the connection. So where will it occur? It will occur in one of the connected walls. So that's a full strength connection. It is designed to be stronger than the expected strength of the weaker of the two connected parts. On the other hand, if the wall is hugely over-designed due to radiation shielding consideration, the demands are extremely low. So for example, you have a 60-inch wall and the demands, and all across the board, your demand to capacity ratios are 0.2 or less. That means that the wall is hugely over-designed, in which case it would make no sense to design the connection between the wall and the basemat for the strength of the wall itself. So we have the option of using an overstrength connection where we design the connection to be the weakest link because it's weaker than the connected members, but it is stronger than the demands that are placed upon it by the earthquake itself. So in an overstrength connection, we detail the connected parts to have ductility, to undergo inelastic deformation, and dissipate energy for beyond design basis events. Clearly, a full strength connection is the preferred option. If your demand capacity ratios all across the board for the wall are less than 20%, you have to ask yourself, why is the wall so over-designed? But if for radiation shielding considerations, you cannot change the thickness of the wall, in that case, you may need to activate the overstrength connection, which I'll show you what it is designed for, what are the demands it has to be designed for. But clearly, full strength connections are the preferred option. Why? Because the full strength connection ensures ductile behavior with yielding and inelasticity occurring away from the connection. So all the yielding and inelasticity occurs in that interior region in the wall, and that's where it dissipates energy. So the full strength connection is designed to transfer 1.25 times the nominal strengths of the weaker of the two connected walls. And I'll talk about that. So if you have two walls that are connected together, then that connection is going to transfer 1.25 times the capacity of the weaker of the two. This 1.25 factor is consistent with ACI 349. It also acknowledges the fact that even for steel plates, you may have actual strength that is greater than the nominal strength of the plate, and you may have some hardening as the system undergoes cyclic loading. And then once you've designed the connection to transfer 1.25 times the strength of the wall, it's additionally checked for the combination of demands that you get from the finite element analysis itself. What this means is that the connection is designed to be predominantly elastic for the design basis. And for beyond design basis, inelastic behavior does occur, but it occurs away from the connection in the connected walls. So that's the full strength connection. For example, I'm showing you here a full strength connection between a wall and the foundation. And what you'll notice is that under cyclic loading, the inelastic deformations occur in the wall. That's how the energy is dissipated. The connection is not challenged. It remains a full strength connection. And eventually, the failure also occurs in the wall itself after dissipating a lot of energy. The overstrength connection, on the other hand, is used when the full strength connection is not feasible. For example, the SC wall is over-designed. This may happen at times for particular demand types. Also, in this case, the connection is designed for 200 times the seismic demand plus 100 times the non-seismic demands. So where does the factor of 200% come from? Why not 150%? Why not 300%? The number of 200% was selected based on a lot of evaluation of what was the purpose of the design. So we're trying to accomplish a high confidence of low probability of failure corresponding to 1.67 SSE. And in order to accomplish that, we found that the connection needed to be designed for about 189% of the seismic demands plus 100% of the non-seismic demands. We rounded up the 189% to 200% to make it a nice round number, but the explanation for that is given in the commentary, and you can take a look at that. The connection is expected to eventually fail before the wall, but it does dissipate energy in the inelastic range before it gets to failure. And then it does need to be checked for the combination of the amplified demands from the load combinations, and the connectors need to exhibit a ductile failure mode. The governing failure mode should be ductile yielding. Experimental verification can be difficult, but it does need to be verified for various demand combinations and thermal loading. So for example, here I'm showing you an overstrength connection here. That's the SC wall. Those are the dowel bars that are going into the foundation. This will not develop the strength of the SC wall. Instead, it will develop the strength of the connection, which actually does behave like a reinforced concrete wall. So when we did the experiment, what we found was that the behavior was governed by the connection region and the dowel bars themselves, which became a reinforced concrete wall for the purpose of this evaluation, and eventually failure occurred in this region after much inelastic deformation and energy dissipation, as you're seeing here, achieving drift ratios of about 2 to 3% before failure occurred in the connection region. So that was an overstrength connection design. When you think about it, you're calculating the connection design demands, selecting a connection design philosophy for each demand type. You're choosing whether you're going to do a full strength or an overstrength connection, calculating the required strengths, and then going about to achieve them by providing force transfer mechanisms, computing the strength of the connectors for each of those force transfer mechanisms, and determining the connector available strength from various references. For example, if your connection involves steel-headed stud anchors, you would use section I8.3 of the specification to check the design. For welds and bolts, you would use chapter NJ of the specification. For compression transfer via bearing, you can use section I6.3 of the specification. And for shear friction, you would actually use ACI 349. Similarly, for the embedded shear lugs and shapes. So let me give you some examples of typical SC connections. I want to show you an SC wall to base mat connection. Of course, your detailing may be different based upon the project-specific considerations and site conditions. As I showed you, you can design this to be a full strength connection where the energy dissipation occurs in the wall, or you can design it as an overstrength connection where the energy dissipation occurs in the connection itself, but it does not develop the strength of the wall. I'll show you an example where you're using a single base plate connection. So here's a steel plate composite wall that has been, and a single base plate has been used in order to accomplish this connection. A single base plate because we're trying to maintain the pressure boundary. This was part of a system which had a pre-stressed concrete containment vessel, which means that there was a liner that was needed all across to maintain the pressure boundary. And that's why this base plate could not be interrupted. I'll show you another version of this connection where that base plate can be interrupted. In this case, if you use a single base plate, the wall is attached to the base plate, and then the base plate is anchored into the foundation using rebars, which are attached using weldable couplers onto the underside. And you need to make sure that you have clear force transfer mechanisms for all of these. And I'm showing you a picture here that identifies the various features. I'll point out these shear studs that are on top of the base plate. They're needed because this concrete is now broken from this concrete by the plate. So you need to transfer the stresses from the concrete above into the foundation. And that's done by transferring the stresses from the concrete through the shear studs into the base plate, and then from the base plate into the concrete below using shear friction. Those are some of the force transfer mechanisms that are coming up. And this has the ability to develop the strength of the wall. So for example, when you're considering axial tension, the ability of this connection, it has to be designed to develop 1.25 times ASFY. That's the tension capacity of the wall. And that tension force is carried by the plates. The plates are welded to the base plate, and that base plate is subjected to that force, and then it is anchored into the foundation. So this would be the clear force transfer mechanism, and you'd have to design this base plate for the associated bending, the prying action, all of that using Design Guide 1, which is what is discussed in detail in Design Guide 32. How do you design it for the tensile force demand associated with this particular design? The base plate has to be designed for any bending stresses and also for prying action. On the other hand, how do you transfer compression? Compression in the SC wall is transferred through bearing of the concrete and the steel plate, bearing onto the base plate, and then from the base plate into the foundation. Since the bending is transferred through a uniform reaction on the base plate, there is some potential for plate bending at the end. This needs to be accounted for, and that's discussed in the design guide, how that plate bending is checked, and the base plate is designed so that this connection is designed to provide the compression force transfer as well. How about in-plane shear transfer? So we're looking at the SC wall here. The in-plane shear is transferred from the steel plate directly through the welds to the base plate, from the concrete portion. So the in-plane shear is carried partially by the steel plates and partially by the concrete. The steel plate shear stresses are transferred by the weld directly into the base plate. From the concrete, the shear stresses are transferred through the shear studs into the base plate. And then that base plate itself is attached to the foundation using these rebars and welded couplers. These couplers may behave as shear lugs depending upon their size. They can get pretty big. Or you can use shear friction mechanism to make sure that the shear is transferred from the base plate into the concrete foundation below. So very clear force transfer mechanisms need to be provided and checked, and those are provided. The entire check, there's a whole calculation of this particular connection in the design guidance, several pages long. We won't be able to go into the details of that, but I'm sure you can download it and look at it. What about the out-of-plane shear? The out-of-plane shear from the entire wall is transferred first using these shear studs. So it's transferred from the concrete to the base plate using these shear studs. And then from the base plate, once again, it goes into the foundation below using either the weldable couplers as shear lugs or using shear friction mechanism associated with these rebar anchors. That's how the out-of-plane shear demands are transferred. How about the out-of-plane moment? The out-of-plane moment in the wall, the flexural capacity of the wall is transferred into the foundation. We take this out-of-plane moment and understand it as a couple between a compression and a tension. Well, luckily, we already did the tension force transfer, right, when we did the tension force transfer mechanism. So this check becomes relatively easy, and all we need to do is make sure that we transfer the compression part of the moment as well. So as you start going through the connection design, some of your earlier work starts helping you in order to make sure that you've transferred all the forces. The detailed calculations of that particular connection design are in the design guide. We won't get a chance to talk about them. Lots of calculations there. There's a 9-step calculation procedure in there. The base plate doesn't have to be continuous. It was continuous for that application where a leak-tight pressure boundary was needed. You can always replace it with a split base plate, which actually makes the concrete continuous. It actually provides you with a nicer force transfer mechanism for the concrete stresses into the foundation. Everything else pretty much works the same. So this is a very nice variation of the single base plate connection and can potentially work really well. In order to complete the design of this connection, we actually had to look at the weldable couplers as shear lugs, and we did some tests. We have some papers on that particular topic as well. Of course, you can also accomplish this connection using rebars. In this case, you're looking at rebars. I already talked about the behavior of this particular system. The test results that were used to look at the tension behavior and really the in-plane shear behavior, those are the two critical aspects, because the compression transfers through direct bearing between the concrete. So we didn't really need to worry about that. This is showing you what those force transfer mechanisms are for tension. It goes into the steel plate, from there into the shear studs, from there into the dowel bar, and from that anchored into the foundation. Clear force transfer mechanisms for various demands, whether it is tension, compression, or in-plane shear. I don't know why it does that. That's the in-plane shear. It's being transferred through shear friction mechanism with these dowel bars into the foundation itself. And that's why we had to do the test to confirm that it works well. There is a splice between the dowel bars and the steel plate, and then that dowel bar is anchored into the foundation, which develops that shear friction mechanism. And it works really well and provides the energy dissipation we're looking for. When you're looking at out-of-plane moment, again, the compression is transferred through bearing, and the tension is transferred through that splice between the plate and the dowel bar. When you're looking at wall-to-wall connections, you need to have these shear studs at that discontinuous to continuous wall interface, because there is an in-plane shear in the steel plate, but there's also in-plane shear stresses in the concrete. The plate can be welded, but the concrete shear stresses need to be transferred, and we're using those shear studs in order to accomplish that force transfer. So you've got to be very careful in how you transfer the stresses from one part of the wall into the other part of the wall. This is a connection that we recommend. We talk about it in the design guide as well. I won't get into too much detail about it, but this joint shear region is very important. And this joint shear has a joint shear strength that we need to be aware of. And the joint shear strength turns out to be 12 times square root of F prime C AC, which we actually get from the ACI publication for joint shear strength. And we show the applicability of that using our equations. I think I would like to show one more connection before I pause and take for questions. And what I'm going to do is actually go down. And that's the connection that I wanted to look at. This is the wall to RC slab connection. And we're looking at a simpler mechanism here between the reinforced concrete slab, which has got weldable couplers and rebars that are located in the RC slab, and then the tie bars and the rib plates inside the wall in order to get that continuous force transfer into the system. This is an RC slab to SC wall connection. We talk about the force transfer mechanisms for this in the design guide, but we don't have a design example for this because it would be fairly long as well. This is showing you how the ties are aligned so that we can transfer the stresses from the slab into the wall and so on. And it discusses the force transfer mechanism when we have tension that we are looking at, or we are looking at in-plane shear, how that is transferred, or out-of-plane shear, how that is transferred from the slab into the wall itself, out-of-plane moment. And it talks about the joint shear that is developed associated with that. So you'll have to read the design guide to see how all of those calculations work out. The PDH code for this session was 16376. We tried to summarize the design guide number 32, which is quite extensive. It shows the application of the N690 S1, including the design of SC walls and the design of SC wall connections, which included connections to the base mat, connections between walls, and also connections with slabs. We have about 10 minutes for questions. Because of that technical difficulty, I couldn't have the whole 15, but please go ahead. And Saj, you can come up here so you can help me answer questions.
I was just wondering, in a traditional building type construction that you will do, you will use this kind of construction for shear walls, so to speak. Does the design guide addresses the overturning moments at the ends? Like, you have so much reinforcements and studs, and then you might have to add additional reinforcement to take that overturning. Does it address any of that at all?
So in a traditional building application, you would have boundary elements, right, in order to deal with that. And I talked about a keyword here. I said that SC walls are labyrinthine in nuclear construction. What that means is there's always cross walls present, almost always cross walls present. So what we do is we distinguish between wall piers and walls. Wall piers are defined, and I have a paper and I presented it last time too. Wall piers are defined as walls that don't have boundary elements. So they are just standalone walls. And the design provisions for that are in a different location. They are in AISC 341 in the seismic design manual. In the seismic provisions, in chapter H7, talks about the design of wall piers because their behavior is different than these. Once you have the cross walls present, the overturning moment just becomes an axial force, tension, and compression into the cross walls. And there is tremendous compression capacity, tremendous tension capacity. So if you imagine that there's really no issue with the overturning moment in a cross wall type situation. If you're working with the building application and you're looking at a high-rise building and you're looking at a core wall, even there you won't use a standalone wall pier. If you did use a standalone wall pier, then you definitely need to go look at the wall pier design provisions in 341, because then you need to think about whether you're going to provide a boundary element. Now, your boundary element can be something as simple as a thicker steel plate. It doesn't have to be really fancy. It depends on what H over L values you're looking at and so on. Some people have used a more circular tube as a boundary element. They've provided CFTs at the ends as boundary elements. It's a lot you can accomplish. That's also talked about in 341. But we distinguish between wall piers and walls in these applications. In most cases, I think you would very rarely use a wall pier standalone by itself, unless you were replacing a concrete shear wall pier. If you were replacing a concrete shear wall pier, you could do that with a composite shear wall pier, and then you'd have to look at the seismic design proposals. Okay. Questions? Yeah. Good.
I want you to go back to the connection region.
Okay. Yeah, well, I remember what it is. Yeah, go ahead.
Okay, you're saying that it was, and that's just from modeling, or I'm just trying to get my head around that versus what I need to provide for that connection. Because if I'm using number 11 bars that I need to develop, they're going to be, if I've got a 3-foot thick wall, guess they're going to be beyond your connection region.
Yeah.
So that's why I was trying to figure out, why is that limit less than 2 tons the thickness of the wall?
Well, if you imagine using number 14 bars,
Yeah.
which can have, you can absolutely do that in a pier construction. Your development length could be about 100 inches.
Right. So
Depending
why-
upon the calculation.
I mean, so
No, I'm still answering. So you could development could be about 100 inches. And if you went 100 inches from here, and 100 inches from here, and 100 inches from here, you'd have an interior region that would be one element located in the middle, right? Or maybe not so. And you've seen this happen in brace frame design, where the gusset plates get to be so big. I mean, there's a famous photograph, right? The gusset plates are so big that you've got a little bitty brace in the middle.
we have that.
You've seen that picture, right? We don't want to get there. So what we're saying is we don't recommend that. So what we're telling the engineer is, if you are going to do that, we don't recommend it. We want the connection regions to be shorter than 2 Ts. Now, if you're saying, well, I have a number 14 bar, how do I develop it? You don't have to use bond between the rebar and the concrete to develop the bar. There are other means, there are mechanical means. So for example, for a number 14 bar, there are terminators. There are different ways, mechanical anchors, by which you can shorten your development length. You got to make sure though that, okay, so you shortened it, but you've dropped off a lot of stresses now into the concrete. You have to make sure that you pick it up into the steel plate. So that mechanism of force transfer has to be there. I think that this is helpful for a lot of people to understand that this wall does have the ability to dissipate energy. How do you accomplish the connection over a distance that is between T and 2T? I think there are other ways to go about doing it. If you find that you're being challenged by dimensions, I'm sure there's a solution. There's always a solution in steel. That's a good question, though. And we were very conscious about that. And even,
Well, I mean, if you've been involved with it, you sort of understand, but if you're using it, picking up for the first time,
Yeah.
those two things sort of, I hope there's a good explanation of the design.
we do have sections in the design guide, but we may not have. So see, we get our blinders on, right? So to us, we know what we are doing, and it may be just a couple of sentences that we still have an opportunity to add a couple of sentences, so we can perhaps mention that. It's not at the typesetter yet. I can always add a couple of sentences to explain that. That's a good point. Any other questions or comments? We saw a lot of connections, and the connections are really the challenging part, because science has got the walls under control in terms of being able to do the design.
The floor connection still is.
The floor connections are complex. It depends on what you're trying to accomplish also. And I think that's the key aspect. A lot of times, people do the models. I mean, and that's what we would do. The engineer would model the structure before they design it. But if in the model, you take the slab model and you just connect it to...
It's fixed.
And so now, you have to design it like that. And then you say, oh, I just need to transfer the shear. Well, then you shouldn't have connected the... So sometimes you can find that analytical assumptions you made months back are coming back and forcing your hand in the design work. And I have made this statement before, and I'll make the pitch again here. What we really need is design optimization. What we're struggling with, I think, in all of the nuclear industry, is that the design has not been revisited after it has been completed. You need to optimize the design. If you do not optimize the design, then you're going to be running around in circles fighting with the constructability of the thing. I think that's been the issue with reinforced concrete. That's also been the issue with optimization of the design is key. And once you complete the design, circling back, we have a section on design optimization in the guide. He completes the wall design example, and he gets to the end of it, and then he goes back and optimizes the design. Because 6-inch stud spacing, the ties that have 3 square inches, it's a lot. So he goes back and revisits, and it's a lot of calculation. It's not easy to do the design optimization, but he does in the end. He gets his utility ratios back up to 0.9 rather than 0.6, and says it can be done if you want to. If you want to, you can optimize it. We do recommend it. I think we're about
out of time. So thank you, everybody.
Good job.